Broadband versus baseband. Let's start with baseband, which is digital, and common baseband cables are Ethernet cables, Cat5 or Cat6. And if you stripped the grey lid off, inside the cable you'd see a pair of twisted cables, of which there may be many of these twisted cables, as indicated by the colour codes on screen. You might see a red, a blue, a yellow, an orange, etc, all within inside that grey lid of that Ethernet cable. Now that grey lid of the Ethernet cable goes into your computer, but all the way down the wire comes an electrical signal, or should I say a single digital signal, which only allows one stream of data at a time, either in one direction, going in or going out. And within this digital signal is digital pulses of different voltage levels, and it's through these pulses that the data gets sent through this Ethernet cable. Now here's a little bit of science about electrical signals or digital signals, where they can only travel so far before they weaken and become unusable or unreadable because of a scientific thing known as attenuation, which basically means that every cable has a limit of distance before the digital signal becomes weak and unusable or unreadable. So the digital signal, as illustrated on the screen by the red signal, as you can see from the troughs, becomes different or wider or weaker as it goes over a longer distance. So here is the key note about attenuation. The exact moment a digital signal becomes weak could happen at any time, but ultimately it does depend on the cable medium or type. For example, Ethernet cables are limited to 100 meters, that's 100 meters, and that's 328 feet, at the point at which attenuation usually hits an Ethernet cable. Now the official definition of attenuation is it only is a problem when the signal degrades to a point that the receiver can no longer distinguish between a 0 or a 1, aka cannot read the data. So now we know what attenuation is. How can we stop or mitigate this? Well, we can use what is known as a repeater device, which looks something like this. And what a repeater device does is amplify a signal over a longer distance so that it doesn't fall to attenuation. So you would probably need a repeater device for an Ethernet cable at every 100 meters to avoid attenuation. So now we have a basic understanding of baseband, let's get a little more technical. So baseband is a single channel or a single signal, and you can think of this like a train track, where only one train can go in one direction at one time. And this is known as bidirectional, which is exactly how an Ethernet cable works, aka the signal can go in and the signal can go out, but it can only go in one direction at one time, either in or either out. And this will become more important as we go through the video because other cables can send multiple signals, not just one signal at one time. But for the purposes, this is how baseband works, and that's the point of this current section of the video. Now this is where we're going to get very technical and go back in history at the same time. You see, whilst Ethernet is a single channel and a single signal, this is true up to a point because recent advancements and even historical advancements means that this is not entirely a true statement. Because there are baseband techniques that can split the current signal on the current single train track into multiple signals, and this is done through various techniques such as time division multiplexing (TDM) or packet switched approaches. But in order to fully understand this, we need to rewind back into history, because baseband being digital is what we use now, but the modern Ethernet cable was not as simple as this. It actually started like this, which was a coaxial cable, and this coaxial cable was used primarily in the 1970s to the 1980s, and it was also known as Thicknet, which was a very thick type of Ethernet cable, and was actually a nickname for 10Base5, which was the standard of what that cable could transmit. But we'll go into that in a moment, but for now just know that Thicknet was the original commercial Ethernet. But it wasn't the nice thin cable that you put into your laptop or desktops today, it was a original thick yellow coaxial cable. And these cables were not just thick and unsightly, they had limitations including the standard of the speed. For example, 10Base5 means the 10 is the 10 megabytes per second transmission speed. The base means baseband signaling, one channel as explained earlier, and the 5 means a maximum segment length of 500 meters, without repeaters before attenuation kicks in. Now, because Thicknet was a thick, bulky cable, computers did not connect to it directly. Instead, they had to use what was known as a vampire tap, which was a little connecting device that would pierce through the yellow jacket of the coaxial cable to touch the inner core of the cable and transmit the data from the computer to the coaxial cable. In this case, a 10Base5 would mean transmitting data at 10 megabytes per second from the computer into the coaxial cable through the vampire tap. And here's a fun fact: the actual connecting type of cable that connected the computer to the vampire tap was known as a AUI, Attachment Unit Interface port, which is not the same as a serial or parallel port, which actually refers to general transmission of data, whereas an AUI is specifically designed for Ethernet networking standards. In other words, the Attachment Unit Interface cable port was designed specifically to work with vampire taps, and if we were zoomed into the vampire tap, it looks something like this. Now here's another fun fact going back even further in history, because we like to give you the full context on this channel. Because you see, vampire taps were needed because coaxial cables were used long before the Ethernet, and long before computing, going back all the way to 1800s to the 1900s, aka before the Ethernet, where coaxial cables were used for many things such as radio frequencies and even cable television, by connecting the coaxial cable from a satellite all the way down into your house to connect to your TV, and these things still exist today, but obviously this is where it all came about. Coaxial cables therefore were the OG of the original internet, aka Ethernet cables, and using coaxial cables for Ethernet was a modern revolution, hence the vampire tap was a workaround at the time to try to use this old technology in more modern technology such as the computing and Ethernet, which was new back in the 1970s and 1980s. And by the mid-1980s there was a new standard that was needed for this Ethernet cable, which came out as 10Base2, which was the evolution from 10Base5. And 10Base2 was a much thinner cable, and it was known as the Thinnet cable, which was the opposite of a Thicknet cable. The standard for a 10Base2 was 10 megabytes per second. As the transmission speed, it was still base, meaning baseband signal, but the difference was the 2, which means the maximum segment length of 185 meters, which was slightly less than a 10Base5, but just slightly, but the cable overall was a lot thinner and smoother and cleaner. And this made it a lot more easier to connect computers to the coaxial cable by using a simplified plug-and-play BNC-T connector, which looked something like this. And it was a lot easier to put the coaxial cable through this BNC-T connector, unlike the vampire tap, which had to be drilled into the coaxial cable. And so it would look something like this, with the computers connecting with a BNC-T connector, as well as the AUI attachment unit interface, the same as the 10Base5. The only difference being that a vampire tap is not needed. Instead, a BNC-T connector is needed to connect the coaxial cable, which is a Thinnet 10Base2. And if we zoomed in, it would look something like this. Now, to further expand on the 10Base2, let's add another node, aka computer, and some BNC terminators at the end of the coaxial cable. And this is what makes what is known as a bus network topology. That's bus, B-U-S. And this essentially means all computers, aka nodes, are connected to a single shared cable. And this bus topology applies to both 10Base2 and 10Base5, even though there are different types of connectors, such as the vampire tap or the BNC connector. The principle is largely the same, that you connect to a single shared cable. Although if one computer goes down, this does cause a problem with this type of topology, where everything will break down, because all computers are sharing the shared same cable, which if broken means all the computers would be broken. However, it's not all bad, because 10Base2 did evolve and make 10Base5 better, because the 10Base2 cable is a much thinner cable known as Thinnet cable, which is easier to flex, and it also uses 10 megabytes per second and is still base, aka baseband signal, but the difference is in the maximum segment length, which is 185 meters, which is the 10Base2, compared to the 500 meters, which is the 10Base5. So with all the benefits of a 10Base2 comes at the cost of a slightly reduced length of the cable. Remember, the 2 means technically 200 meters, but for some reason they said 185. but ultimately it's just a reduction of the maximum segment length. So that explains 10Base2, but eventually this was no longer needed and these problems became serious problems, so this cable was removed and a new alternative was needed, which was the Ethernet cable, which we spoke about earlier. But before we get to that, let me just finish this section about coaxial cables, because now we know about 10Base2 and 10Base5, there are some important technicalities that we need to know and would be useful for both your exam and your general life. Because even I had to troll the internet in order to find out this information, which isn't really clearly explained, but I guess that's because it's history, but nonetheless it's still important, and on this channel we like to give you the full context. So to recap, the two types of baseband cables or coaxial cables explained were 10Base2 and 10Base5, and each of these cables carry a single digital signal which takes up the entire bandwidth of the cable to just transmit that one signal. And these baseband coaxial cables are used for older shorter distance digital Ethernet networks, and the types of cables you'll commonly hear in this band are RG8 and RG5858. And the keynote here is that these type of baseband coaxial cables are generally 50 ohms OHM cables. Now the ohms will become important as we explain the concept of impedance, which is quite scientifically technical. But in order to explain impedance, we need to understand that baseband coaxial cables are not the only type of cables. There is actually broadband coaxial cables. Now these two types of cables are totally different, so baseband and broadband do not work the same and have different frequencies and electric ratings such as impedance, known as ohms, OHM, and these dictate how the cable technically works. And fundamentally there is a huge difference in that baseband is only one channel, whereas broadband is multi-channel, aka multiple signals at different frequencies can be sent through the same wire. So you can think of this as a road with many lanes. Now to clean the screen up a bit, I want to talk about another key term, so let's bring back these two analogies of the train track and the multiple road lanes, covering baseband and broadband signals. Now baseband signals and broadband signals are different, in that baseband can only carry one digital signal, whereas broadband can carry multiple signals which can be analog or digital, and these can be sent simultaneously by dividing the cable's bandwidth into different frequency channels. And this frequency is a key point that will loop us back to the original point in the video about baseband and time division multiplexing. But just before we do, we need to understand what came after 10Base2. So to recap, we know that baseband started with 10Base5 cables, which then was later replaced by 10Base2 cables, and these were coaxial cables. But how did they then turn into the modern Ethernet cables that we know today as twisted pair? That is the million-dollar question, so let's answer this question now. So what succeeded 10Base2 was 10Base-T. But before we go into 10Base-T, let's just remember that 10Base5 was Thicknet, 10Base2 was Thinnet, and 10Base5 was the original Ethernet, which came out in 1983 as part of the IEEE standard 802.3, which then became 802.3a in 1985 for 10Base2, and later became 10Base-T in 1990 for IEEE 802.3i. And 10Base5 was a thicker cable that supported 500 meters before attenuation, whereas 10Base2 was thinner and supported up to 185 meters, and both of these two types of coaxial cables had different types of connectors, being a vampire tap for 10Base5 and a BNCT connector for 10Base2. Now both 10Base5 and 10Base2 used what was known as a physical bus network topology. As explained earlier, that means all the devices, aka computers, connect to a single shared central cable, or the backbone or bus, rather than having a central hub or switch. Everything is just connected to one single cable, one line. That's where the vampire taps and BNCT connectors and terminators and all sorts of equipment was needed to connect to this one single cable. But ultimately this bus topology meant it was a single point of failure, meaning if the single central coaxial cable backbone is cut or broken anywhere along the line, the entire network segment stops working. So that was one downside, but here's another keynote. There was also another downside around communications, and this is where CSMA CD came into play. You see, if computer A was sending a signal and therefore using the entire line, computer B would have to make sure they listen to the line to make sure the line is clear before sending their signal to avoid collisions. And this is exactly what carrier sense multiple access with collision detection is all about. And this was great at the time in the 1980s, but eventually the internet and the world and people evolved. That meant more resources and requirements needed on the bus topology, which was becoming an overhead, so a new solution was needed, and that's where the world moved towards 10Base2 and going back to the traditional phone lining type cables, or twisted pair cabling, which I'll explain in a moment, but it was a big shift away from coaxial cables. But coaxial cables still exist then and still do today, but for very different purposes. So 10Base2 moved towards what was known as a star model, or a star network topology, which meant instead of having one long coaxial cable that was a single point of failure, why not have a device in the middle of all the devices that can control this in a more efficient way, whilst also retaining the CSMA CD, carrier sense multiple access with collision detection, almost like a centralized theoretical hub. And that is exactly what happened. A device known as a hub was invented. Now, a hub was based as an evolution of the original repeater device explained earlier in the video, which, as a recap, was a specialized hardware device used primarily to amplify signals in the coaxial cables of 10Base5 and 10Base2. And so, as networking transitioned from the physical bus network topology of 10Base2 towards a more star topology of 10Base2 using twisted pair copper wiring, which were the additional ports on the repeater device. These were Ethernet ports as opposed to the coaxial ports, but for illustration purposes I'm just putting all the ports. And these ports were multi-port repeaters, and it was marketed to consumers as a network hub, which could be put into a middle of a star network topology. Now, over time, the coaxial cable need was eventually phased out, and this network hub became an Ethernet hub, using an Ethernet port, which is known as a 10Base2, which used RJ45 connectors, and BNC ports 10Base2 were still there but eventually were phased out from around 1993 to 1995, after which pure twisted pair 10Base2 RJ45 Ethernet cables took over. And so the transition from repeater-based bus networks or repeater hubs switched over to network switches, which occurred around the 1990s and early 2000s. And the switch device would become the central hub point of the star network, which moved away from the bus topology and into the world of Ethernet and RJ45 10Base2. And it's worth noting that 10Base5 and 10Base2 are totally different type of cables compared to 10Base2 in both electrical and frequency ranges and characteristics. But to confuse matters, both standards transmit the exact same speed of 10 megabytes per second, and they both utilize the same Manchester encoding scheme, which allows frequencies of up to 20 MHz. But 10Base2 is a totally different physical type of cable, and in the 1990s it was known as unshielded twisted pair UTP, which was a Cat3 or Cat5 type of cable with an RJ45 connector, and this used to be used for regular twisted copper telephone lines, totally different to coaxial cables. So you might be wondering then exactly what was the benefit of using 10Base2, aka the phone line type of cables, over the coaxial, because all else seems equal? Well, this is a very good question, and it comes down to a very important keynote. The primary benefit of using 10Base2 came from its network layout, the topology, the star topology with the switch in the middle, which was originally a repeater hub, and also the wiring structure being the twisted pair was a lot more efficient than using coaxial cables for the purposes of internet and Ethernet data. Now, I want to look back to a point I mentioned at the beginning of the video around time division multiplexing. You see, now that we understand that Ethernet came from coaxial cables which did use time division multiplexing, TDM. But when the Ethernet changed to 10Base2 and twisted pair cabling, then the Manchester encoding scheme and the CSMA CD carrier sense multiple access with collision detection combined gave the same equivalent of TDM for the star topology, which then used the 10Base2 Ethernet RJ45, which was an unshielded twisted pair UTP. And there you have it, folks. I hope that all made sense, as we got very technical, and there's a lot more to this, but I won't carry this video on. I will make a separate video at your request if you want to learn more about this topic. Please let me know in the comments below, and if you did enjoy this video and found it useful and informative, please be sure to like and subscribe if not already to help support this new channel's growth. As ladies and gents, there is no way for myself and YouTube to know that you are enjoying these videos without your kind likes and subscribes. And thanks again for watching.